Okay. So anyway, thanks for coming. This is a kind of a follow-up to the last talk on Scala Z. Today we're going to be talking about this thing called the state monad. So the plan today is I'm kind of going to describe what the state monad is, but we're going to derive it. We're going to start with just regular-looking, classic object-oriented style Scala, and point out some problems with it when we try to remove state mutation from it, and then I'll derive the state monad. And then in the second half of the talk, I'll point out how it's provided by Scala Z, and how it integrates with the rest of Scala Z, and at least give you some jumping off points to go learn more about the way it integrates with other stuff. So we're going to start simple. We're going to create a web service. The idea is that it pulls statistics about a particular user on a social media type website, and gives you like the number of followers they have or the number of people they follow. The initial plan for this example is I was going to pull GitHub statistics and show you like number of projects you follow or people you follow or whatever. But the code examples for actually doing that kind of took away from the point of why we're all here. So we're not actually going to write the HTTP code today, but let's take a look at this interface. We have a social service with one method, follower stats, taking a username, and we just get back follower stats with num following and num followers. Right? Very, very, very basic. And we can implement this in a stateless way. Just replace that comment with your HTTP code of choice. Whether you're doing HTTPS URL connection or you're using something like dispatch or whatever, nothing particularly interesting here, right? So now, let's say we're running this and we realize we're calling this method a lot, and we want to put a cache in to say, in my app, if I call this method 10 times in a 10-minute period or 5-minute period, I want to cache the responses for up to 5 minutes. So how can we implement that? This is kind of the classical way, object-oriented programming. This might be how we attempt this, right? In our classical Spring-style architecture, maybe this is how we do this, right? So we would introduce a new mutable cache. Now maybe that's a big mutable map, or maybe it's some fancy data structure that supports concurrent access or whatever. But we'd introduce a new field on our class, right? And our follower stats method would probably look something like this. We would check the cache for that particular, for an entry with that particular username. And if the response exists and it's not stale, we would return that value. And if it exists and it is stale, or if it doesn't exist at all, we would go call the web service, update the cache, and return the response. Make sense? So, this is okay, but we have that big mutable cache in there. And the question here, at least you came to this talk, so you must be interested, is like, how can we do this in an immutable way? How can we do this in a style that's using more functional programming techniques and less embedding state way down deep in my application wherever this thing happens to be used, right? So let's take a look. What are we doing here? If we kind of just look at the essentials, we have something where we're getting from the cache in the start of the method, right? And in the bottom of the method, we have something where we're writing to the cache and returning some unrelated, or some value, where that value really has nothing to do with the cache itself. It's the value we're sticking into the cache, but we're returning that value to the callers, and we have this side effect of both reading and writing to this kind of background object, this cache object. So we could kind of change the language there a bit and be a little more immutable and say, instead of saying, down below we're going to write to cache, we could say just create a copy of the cache with the new value, right? And then as an output of this function, instead of actually returning just the value, we could return the copy of the cache in addition to our value. And so you end up with something like this, right? When we look at that particular function we started with, follower stats, and we look at like how can we make that purely immutable, my argument is that this is precisely the simplest approach to doing that. right? I had one piece of data I was mutating. In this case, it's this cache, object. And if I make that cache object immutable, in order to read from it, I've got to pass it in, obviously. And in order to change it, I'm going to copy it internally and return it. There's no simpler way, is my argument, to implementing this in a purely immutable way. So that makes sense. Right, like there's no special magic. Like it is literally the definition of, if I have this immutable cache object, the bare minimum thing I could do would be to read it in and return a copy of it. And that's exactly what we've encoded with this method signature. So there's nothing like fancy. There's no special approach we're taking to handle that. So we can implement this method. And so maybe, here's one particular implementation that uses pure Scala. We're going to create two helper methods, check cache and retrieve. Check cache, let's look at the signatures first. Check cache, given a username as a string and given the cache, it can return you back a modified cache, and it can also return you an option of follower stats. And all check cache is going to do is say, if that particular user is in the cache, return their follower stats in a sum. And if they're not in the cache, return none. And retrieve, similar, given a user and a cache, all this particular one's going to do is actually make the web service request. Okay? As a result of making that web service request, we're going to return the follower stats we got back. We'll also return a cache that's already been updated with whatever we just retrieved. Okay? And then if we have those two helper methods or functions, we can write this follower stats function. So the idea of the follower stats function is we're going to call check cache. We get back a new cache C1, and we get back an optional follower stats. Right? In this case, we're pattern matching on that optional follower stats, and we said if we got back some fs, then return a tuple of our output cache C1, the updated cache from the check cache call, as well as the actual follower stats we received. And if we didn't get back anything from check cache, we're going to go retrieve it from the web service. Does that make sense? As a side note, I'm not doing anything with I/O today, or this is not purely functional code because we are, theoretically in this code we're going to go to a web service. So it's not really the focus of today. And here's our implementation of the check cache. So we have this cache object. It has a get method that takes a string, the username, and it returns you an option of a timestamp of a value, an optional timestamped value. So in this case, we're saying if we got back some timestamped follower stats that has a timestamp TS, and that timestamp is not stale, if that's true, then return a copy of the cache, and we're going to increment the hit counter. And say in this particular case, you asked for something from the cache, we found that thing in the cache, and it was not stale, so we're just going to track the fact that our cache was effective here. And we're going to increment this hits counter with the c.copy. Then we're going to return some fs as our actual important value here. And then in any other case, either you had some timestamped follower stats or you had nothing in the cache for that username. We're going to just say update the cache and increment the misses counter and say none for the value. Make sense? So still all plain old Scala. And then finally retrieve, pretty simple, right? For retrieve, we're actually going to call the web service for that username. We'll get back a follower stats object. We're going to wrap that follower stats object into a timestamped data structure, and we're going to timestamp it with the current time now. And then we'll just update the cache. We're going to say, cache, update yourself. For this particular user, here's the timestamped value. Presumably, update is a method here that's returning you a copy of this cache. And the follower sets itself. Any questions so far? So okay, we did meet our goal, right? We got rid of mutation from that initial service. We had to kind of had this explicit state passing thing going on, where like anything, our state values themselves, anytime we want to read them, we had to pass it into a function. And then we had to change all of our return types to tuples, where the mutated state was one of the outputs in the tuple, right? So very simple, right? We have no custom code here. There's no libraries or anything there. Very basic Scala, and pure immutable. But this is kind of ugly to work with, right? And it's error prone. So let me show you an example. I was working on this slide when I was preparing this. I think last Thursday I was working on this slide. And I wanted to make this point. And so I started highlighting these C and C1s in this slide. And as I was doing it, I found the bug I was trying to talk about. Like, I knew I wanted to make this point, yet when I, off the cuff wrote this code to run, to do this presentation, I actually wrote the very bug that I had a plan to talk about. So anyway, it is very error prone. The idea here is that you're explicitly wiring the input and output states, function call to function call to function call, right? You start with some cache coming in, you got to pass that to your first function, get a new cache coming out, take that cache, pass it to the next function, etc. And it's kind of like wiring or weaving that through all your code. So, in this particular example, my bug was in that case none retrieve u. I had retrieve u comma c. So and that compiles, right? What would that do? If I had retrieve u comma c on that case none, what would happen is when we first came to file our stats, we call check cache. Check cache, remember, is going to say, oh, well, this particular user, we don't have any cache data for it, so we're going to increment the misses counter. And we're going to increment misses to 1 for the cache. But now that's a copy. So C1 is the object, that is the cache with misses equals 1. But then down here I'm going to say match on the value that was returned. That hits the case none, we call retrieve. We pass C into retrieve. And as a net result, we'll get follower stats back, but we're going to lose the fact that we had a cache miss. Right? And this is very simple to do when you're refactoring methods, reordering the way they're called. Code that maybe was right the first time you wrote it, all of a sudden still compiles. And if you didn't have proper test coverage for that, you're going to have a big problem. So how can we do better? The basic idea here is we're going to represent state as immutable value, or as immutable values. Don't hold me too strong to this pure functions concept because I'm doing I/O and all that. But ignoring that part of it, we want pure functions. They're going to need ways to read state, write state, compute values based off that state. And the simplest way to represent is that type signature. Right? So this is basically just what we worked on. That type signature makes sense, right? So consider this. We're going to have a new data type. We're going to call it state. It's generic when S and A. So we have a state type and we have a value type. And we're going to have a couple different methods here. The basic idea here is that state is going to wrap a function from S to tuple SA. That's all it's going to do. It's just be a data type that wraps that. In order to invoke that function, the function that we wrap, we have this run method. Right? So run's pretty obvious, right? If state just wraps a function from S to SA, and run takes an S and returns an SA, all run's going to do is invoke the function, right? So at least so far we've done nothing. State with just run doesn't really do anything for us. It just obfuscates the function call. And in fact, we're going to have an apply method on the companion object that lets us take a function S to SA and just lift it into a state, right? So look at the signature of apply. It just says, given some function f that has that signature from that previous slide, S to SA, just return us this state object. Now, of course, if I did state.apply and I passed a function in, and then I immediately called run and just passed a state in, that's completely isomorphic to just calling the function, right? Nothing fancy. There's kind of an interesting thing here because I haven't showed you the implementation of map and flat map. But if we fix the state type S to a specific one, like in our example it was cache, then the resulting data type that has kind, basically a type constructor of one type, ends up actually following all the monad rules, assuming we implement map and flat map a proper way, which we're going to do. So let's take a look at that in depth. And I'm going to come back to that point, so don't worry too much about that point. How are we going to implement apply? So the idea of apply is we got this function, we need to return a state. So we're going to just return a new anonymous implementation of the state trait. And we're going to set the run method equal to just invoking the function. Right? Very basic there. Now, what I didn't show you here is that all those other methods are not going to be abstract. We're actually going to implement those in the trait. So let's look at those other methods. The trait itself will leave run as abstract. And now we have to implement map and flat map. So the first question is that, let's think about what we have with map. Map, we're given a function from A to B. And we want to apply that function on the value that's returned by evaluating or running this state. So I have a state S of A. That's my trait itself. I'm going to call map and pass it a function that converts an A to a B. And now as output, I want state SB. How could we do that? So one way we could do that is take the function that we're wrapping, which remember has the signature S to SA. We could run it with an input state. So if I have an input S, I can run it and get back an SA as a tuple. And now all I want to do is get that, I have that A value. I can evaluate F. So I can apply A to F and get back a B. Not always. Like in this case, we were actually doing like a conversion from option to non-option. Right. But yeah, I mean, you could, like F could be A to A, and that would, apply here. You just got to get another state SA. But we can actually implement this like that, right? I mean, and it's basically what I just said, but there's a little weird thing where that, like, remember the description was that if we have a starting S, then we can call run, invoke the function, get back an S and an A in a tuple, take that A and apply it to function F and get a B. Now I have an S and a B in the tuple. Well, that's still not really what I wanted because I needed to back a state. So I have two problems with my description. One is that I don't have an initial S, and the other one is that I need a state in the end, not a tuple. And so if you think about it, what I described really is a function from S to an S and a B, right? If I just say I need an initial S to run this, and I don't have it, so I'm just going to make it a parameter to like a lambda. Now all of a sudden, my lambda expression becomes a function from S to SB. And if I have a lambda from S to SB, I can lift it into a state. And so that's basically what this is doing, right? The syntax, if you're not familiar with the syntax, state open brace is just a syntax where I'm going to call state.apply and pass it the lambda represented by those braces. The lambda represented by those braces is saying I've got some anonymous variable, or some variable S, and then internally, when this function is actually executed at some point, when the resulting state is actually run, internally we're going to run the initial state, pass it that initial S, get back S1, comma A, and then return S1, comma F of A. Okay? And don't worry too much if that isn't quite clicking yet, because this is the derivation of state, and to use it, you don't really have to necessarily understand how to implement map, although I do think it's illuminating. So we have flat map. And flat map, given an A, or given a function that takes an A and returns a state SB, we need to return a state SB. And so the idea is basically the same, right? We're going to use a lambda expression lifted into a state. Given an initial S, let's just run the inner function. That gives us back an S1 and an A. So the first two lines of that implementation are identical. But now when I take that output A and apply it to the function F, I get back a state SB, right? And so if I have a state SB, but I really need to return overall a state SB, in the lambda, if it's returning a state SB, I've got a state of a state. That's no good. And so anyway, I could just run that inner state, right? So if I just run the inner that inner state, the state SB, and I give it the S1, the state value returned from that first run function, I end up getting back the right thing. I end up getting back, in this case, a tuple SB. So anyway, that's kind of interesting because you can see this pattern of this lambda took an input S, it ran a function and got an S1 out, and then passed that S1 into another state. So you can sort of see that wiring I was talking about, right? So let's try to use this stuff. Yeah, sure. Yeah, I mean, so in this particular case, this presentation of the state data type is inspired by the Scalaz encoding of it. Oh, and for anyone, the question was basically, what's the implementation at run here? So the idea in this case is that state itself would be a trait. Run is an abstract method. It's not defined. And so the only way to actually get an instance of this trait is by calling the apply method on the companion object. And the apply method on the companion object just says, yeah, given an S to a tuple SA, we are going to return a state SA. And the way we're going to do that is by anonymously subclassing, basically, or anonymously instantiating that state trait and defining the one abstract member. But yeah, all it does is call f of s. I'm not sure why I said I there instead of s. That seems kind of strange. Now, I mean, the why is that particular encoding? Why are we wrapping it? Why do we implement that map in flat map? Is not particularly obvious yet. So we're going to walk through our code and refactor it and try to use state and see what happens. Okay. So this is what we had, right? We had these three functions. We passed cache in, we got the cache out. So we're going to try to refactor this to use that state data type. Well, these don't have the shape S to SA, right? So right off the bat, we're kind of in trouble. Follower stats takes a string and a cache and returns a cache and a follower stats, etc. So how can we kind of refactor these to force them into that shape? Anyone have any ideas? What if we partially applied them, for instance? Right? We could apply just the username to follower stats. And if we apply just that username, we get back a new function that takes just a cache, right? And returns a cache count of follower stats. So what's a nice way to support that syntactically in Scala? There's our S's and SAs, and so we just want to get that shape right. We can just do that. Right, so let's look at the two slides. This was our normal function, and all we did is create that single parameter list. We turned it into two parameter lists. And you wouldn't even really have to do that, right? I can just partially apply this function. I can take follower stats, give it a string, and use an underscore for cache, or put an underscore, use an underscore for cache. Effectively, what I'm doing is creating a lambda expression that, given a input cache, will invoke follower stats with those parameters. But syntactically, that's a lot of noise when I go to try to use it. And Scala has this nice multiple parameter list to functions feature, where I can just call follower stats with a string. And as a result of that, I don't have to pass the second parameters. As a result of that, I get back my function from S to SA. Okay? So here's our function implementation for follower stats. Let's make that refactoring. We converted, I'm going to jump back and forth between these two slides. We first want to convert the signature of the function itself into the two parameter lists. On the first line, we were calling check cache, passing U and C, and we got back that val. We pattern matched on that val, and then, in the case of none, retrieved, otherwise returned. So we could do something like this. Check cache with just the username applied gives us back that function S to SA. We can wrap that function S to SA in a state. So state paren check cache paren U, right? That gives us back a state whose A is the output type of check cache. Is the output value type of check cache. Remember, check cache is an option follower stats as its value type. Okay. So if I partially apply check cache and I lift that value into state, then I can use flat map. And if I use flat map, I'm given the A, right, as the optional follower stats OFS, just like on the previous slide. And now internally, I can pattern match, just like before. And in the case that I got a follower stats, actually, let's do the none case first. In the case that I don't get any output from check cache, I need to retrieve something from the web service. Now, if I retrieve something from the web service, the way I have to do that is I have, remember, retrieve, I can give it a username to get a partially applied function from cache to cache follower stats back. And since I'm flat mapping, the result of my whole closure here needs to be another state. And so if I have this retrieve, that when I partially apply with a user can give me cache to cache follower stats, I can wrap that retrieve into a state, and now I have a state whose output A value is follower stats. And that's what I needed overall, right? So anyway, so the none case is pretty straightforward. Once you kind of get used to partially applying these functions and lifting them into states, which comes pretty naturally once you get used to it, the none side's pretty straightforward. Now the sum side's kind of weird, right? Because the sum side, we have the value we want to return. It's FS, right? But that doesn't type check because in flat map, again, I have to return a state. And so how do I lift just like a single value? It's not a function, it's just a value, FS, into the state. And so we do this. We basically say, let's create a lambda that given some state S, we're going to close over the FS value, and we're going to return the same, whatever you gave me, we're going to return the same thing you gave me as the state value. And of the actual value, we're going to return FS. Right? So that little lambda, then, the inner S2 S of F, or S comma FS, we just wrap into a state and lift. So it's a little weird. The net result of this expression, starting on that first line of implementation with the word state, down to the second to last line, is now a state from with the S type fixed to cache and the A type fixed to follower stats. But I need to return S comma A here. And right now I've got a state. Right? If I call flat map, I always get a state back. So I got to run it. So if I just run that state, passing the C that was passed to me, I get back, C comma, or a cache comma follower stats. And everything just works and lines up. Does that make sense? Yeah, so the idea is follower stats. Look at the signature. The return value of follower stats is cache comma follower stats in a tuple. But if you look at the expression that, basically everything up to that dot run, the type of that expression is state of cache comma follower stats. So I have a state of cache comma follower stats, and I need to get that to a tuple of cache comma follower stats. And the simplest way to do that is just run the function, giving it an initial state. And I have an initial state because I have that C as a parameter up top. So I sort of, what I did here is I wrapped check cache and I wrapped retrieve. I lifted those functions by partially applying them. I lifted those functions into the state data type. I flat mapped them together, effectively, with some details about that sum and none. That gives me back a state, but I don't need a state in my API. I need the actual values, so then I run the state. So the only reason I ever put them into the state data type was just to remove the explicit wiring, just to immediately turn around and just evaluate them. So a couple minutes ago I said something about how if you took a state, lifted a function into it, and immediately ran it, it's isomorphic to just running the function. And that's true. It's kind of useless. Unless you're trying to hook multiple functions together through the state and get that wiring. So the net effect of the state data type, the state monitor we've created, is that we can wire those input and output states together through a series of sequential functions and not actually have to pass them around manually. Now, if this was like the end slide of the presentation, you all should throw stones at me, because this is not that much better, right? Arguably, it's much worse than where we started. So we're going to keep going, keep refactoring and see what we can do. But not by adding any more features to our data type. So the next step is like, what is this run thing? Can we just get rid of run? Let's try it. If you just strike out run, the net result of this thing is a state. Well, I can just change the signature. I'm sort of cheating, right? But the idea is that before, the signature of follower stats was my second parameter list is a cache, and I'm going to return you a cache comma follower stats. How about I don't take that parameter and just return you a state? Because that's what state's encoding, right? State's encoding a function from cache to cache of A, in this case. So I get rid of run, my inner expression returns me a state, and then I just strike the parameter from my parameter list. And now, as a result of this, I'm going to have to change the output type of follower stats from, tuple SA to state SA. Right? So that's all we did in that step. Now we're going to do the same thing on those inner functions. So here was our check cache. I've already made the partial application thing here. I've already changed the parameter list, so we've got U in the first parameter list and C in the second parameter list. But otherwise, this is the same. So let's just kind of go through mechanically and make this change. And this is kind of the key point from that last step. This is all we did. Like, look at the difference between these two lines. It was this of cache and then returning a tuple. And all we're doing, this is completely mechanical, is getting rid of the second parameter list and returning a state itself. Okay? And now the body itself has to be lifted. So notice here, this was just your normal looking function from before, nothing fancy. We're going to strike C, change the return type to state, and now make the body a lambda expression that says, give me a C. Right? But the rest of the slide didn't change. So again, you could write a macro to do this in your editor. We'll do the same thing with retrieve. So again, you've got that second parameter list returning the C comma S, or S comma A, sorry. And we'll just change, strike the second parameter list, change the return type to state, and create a lambda expression for the inner function. Right? Now that we've done that, this code's not going to compile, because we changed the return type of those two helper functions. Right? Before those helper functions, we were kind of doing two things. One, the helper functions return types, when fully applied, was the tuple, right? And the other thing we were doing here is we were partially applying them, so we'd end up with a function from S to SA. Now that now that those functions are no longer being partially applied, they only have one parameter list again. And the net result of calling that is that we get a state back. We got to change this function. And the only way we're changing it is just removing the state wrapper. Right? Okay. A little better. What can we do now that we have these inner functions as states? Now that these inner functions return state data types, can we use these in some way? So what does Scala have to help us when we have methods that have, or sorry, data types that have maps and flat maps? What syntax do we have? Right, like for comprehensions, right? So we can use these things in a for comprehension. Okay? Again, completely mechanical here. But what we saw is that we've got a check cache call that's returning a state. We're calling flat map on that and passing it a closure that has, that's binding this OFS variable, and then using this OFS variable down below, we can just convert that to a for expression. Okay, this is getting better, right? Exact same code. The sum and none did not change, by the way. Everything in that match is identical in these two slides. The only thing we're changing is that instead of calling flat map directly, we're going to use a for comprehension called check cache as the initial generator and bind its inner value type to inner value that it's returning to OFS. Now that's an A, right? We get to ignore that state value that's being passed around through everything. The state monad, the whole point of it is ignoring that value, letting it, be implicitly wired by the data type. And then I can just use that in the next generator. Since my first generator returned a state, my second generator must return a state. We already knew that anyway because the way we were using flat map, like I talked about earlier. So anyway, the second generator, in the case that we got sum fs, returns that weird state that just wraps a value, ignores the state and just wraps the value. And in the case we got none, it calls retrieve, binds the output of that to fs, and then just yields fs. Okay? Make sense? So, this is sort of this is what you should expect in a presentation about the state monad. There's no cons, right? Everything's a pro now. And clearly that's not true. I mean, there's performance impacts of doing this. There's a lot of flat maps occurring all over the place. I mean, there's, in a toy example like this, there are certainly cons. But let's look at the pros, right? This is still, in my opinion, still meets the simple test. And the most complicated thing we did here is passing around functions. And I know, if you're not used to passing around functions all the time, that is a bit of a adjustment. But as soon as that clicks, that was the most complex thing. No fancy magic, no implicits, no subtyping, I mean, nothing, right? Very, very, very basic Scala. Everything's immutable. We've got all that state wiring happening automatically. And we've got these for comprehensions that, at least syntactically, let us sort of write, top down, sequenced, do this, then do that, then do that, then do that, with all the state wiring happening. So it's a pretty good one. So let's talk about state combinators. So what was this weird thing? Go ahead, Jack. Yeah.
Normally when I see a match.
Oh yeah, that ugly match on sum and none. Yeah, it is coming. The question basically is, and tell me if I'm wrong, the question is basically, why did we pattern match on the option here? That's kind of a code smell. Shouldn't we be using like higher order functions on option? And yeah, I wouldn't write it this way in reality. The reason I did this for the first set of examples is because I didn't want anyone who's not familiar with using fold on option, for example, to kind of get lost in what was happening with the way all that comes together. We will rewrite this to use fold later. Okay. But yes, you could just map and get or else as well. It would have been effectively the same thing. So let's look at this thing. So this was weird, right? Given sum A, in this case fs, we want to wrap that fs in a function from s to sa, completely ignore the input s, just pass it through, and then wrap that in a state. It turns out that happens, or that is pretty useful and happens a lot. So why don't we refactor that into a method? So let's have this method called state that basically just says, given some value a, let's just lift it into a state of SA. Same exact code between two slides, right? All we've done between this slide and that slide is wrap that inner thing into a method called state, and we made the value type generic. We parameterized the value type, right? Make sense? So now that I have that function, I've got a way generically to say anytime I have a value, I can wrap that value into a state for some state type S and some and the type of value that matches the value, the type of value I have. Okay. This is not particularly useful yet, but short of what we saw already. Yeah, go ahead. Yeah. Sure. Yeah, good question. So the question was for folks that aren't, used to closures in Scala, basically. Lowercase s there is actually a lambda expression, a function of one type s, or sorry, a single value s, that when evaluated will execute the right side of the arrow. Now, it's not typed there, right? There's no explicit type right there in that code. So what is the type of s? Yeah, the brace is a lambda expression, yep. And this is just the parameter to state.apply. And anyway, Scala is inferencing the type s there based on the surroundings that it's in. So. Now here, when we don't have those surroundings, we're going to have to define, when we define the state method, we're going to have to define s and a to be parameters to the state method, or the state function. The internals of state itself, again, can be inferenced in this case, right? Because we said the return type of this function is state of SA, and the inferencer can say, okay, well, there's this one expression state. State.apply is parameterized on S and A, and the inferencer can hook it all up and say, okay, that means this inner closure here has to be of type capital S. Does that function make sense? So, okay, we can use that now. Obviously, right? That's why we defined it. So given some fs now, we can just call state.state on fs. And then we're going to get rid of that, to Jack's question, we're going to get rid of that ugly pattern match on option. In this case, we're still staying in the realm of plain old Scala, no libraries. So the best way to convert that in plain old Scala is a map with a get or else. And it turns out that, due to limitations, at least in the inferencing algorithm in Scala 292, when we call map in this way in the point-free style, the inferencer can't figure it out. Now, in this case, we're calling map in a point-free style, right? We're saying, notice we're calling state.state, but we're not passing it an A directly. So the net effect of calling state.state and not passing an A is that that's a function from A to state SA. Map gives you an A, and so calling it in the point-free style, it does what we want, but the inferencer does get a little confused. So in this case, we have to explicitly tell it the two types of S and A. Okay. So that was kind of an interesting combinator. And the reason I call it a state combinator is that it's a function that lets us work, there's no point in calling that function by itself unless you're already working with states. But when you're working with states, you do run into these cases like we did, where we had this one single value and we needed that to interact with the rest of our program. And so it was a function that let us effectively instantiate or construct a state based off of some other value. So there's other really useful combinators. First is get. sometimes called init too, although I really don't like that name. At least for my own, personally, it's just I find it confusing. But for get, I don't have any problems understanding that, right? So the idea of get, the closure that it wraps just takes the state out of the state side and also sticks it on the A side. So look at the type you get back. You get a state s comma s. Okay? So think about it. If I've got some big expression where I've got that state of a cache of some value, like follower stats, but I actually want to, in some function somewhere, say, no, I want to directly reference s. I want to maybe pull the hits value out and print it out or something. The whole point of what we were doing with state was hiding that value s and implicitly wiring it through everything as I was calling functions. And this lets me get it back out. I can kind of get another reference to my current state value on the A side. Right? Make sense? That one's don't worry about yet how you're going to use these. I'll show you that. But does that implementation make sense? There's getS. Same exact idea, except maybe a lot of times when you go to pull a state from the S side to the A side, maybe really you're just doing that because you want to pull some, you want to compute some value based off of that state, or you're going to pull some inner piece of data off of that state or something, right? So let's just do that in one step. So if you give me a function from S to A, which could be the identity function, right? If you give me a function from S to A, we can return you a state that still takes the input state, returns it as the output state, but whose value that it computes is just the result of taking that state, applying the function to it, and getting it out. So anyway, if you call getS and you pass identity, that is get, right? Here's a weird one. Put. What our put combinator is going to do is that given some input state S, we're going to ignore it. Completely. Look down below. Sorry. Let me rephrase that. Our put combinator, in order to create a state, you're going to construct a state. In order to construct that state, you're going to give it an S. You're going to say, put this new S into my state. And when that state is actually run, what it does is it says, ignore my input state completely, and just on the output side, just replace it with the S that they passed me when they constructed me. Forget the unit thing for a second, I'll explain that. But does that sort of make sense? Let's see how the way the state closure, in this case it says underscore, it doesn't need to even bother to bind a name to the input parameter because it's not going to use it. Right? So as an example of put, and we'll use put again in a minute, but as an example of put, like I could have been using that program we wrote, accumulated all sorts of stuff in my cache, and if I wanted a way to reset the cache back to be a completely new empty cache, I could have just used put with cache.empty. Right? And then when I combine that resulting state with the rest of my program, whenever it gets to that part in running everything, it'll just throw away whatever we've accumulated so far and start over with whatever I pass it. And the unit part of that basically says, well, there is no value here. Yeah.
Suggestion was yes.
Right. Oh, yeah, I see what you're saying. Yeah, that's a good point. Yeah, that's confusing. Right, yeah, we're effectively ignoring the input state, but so the S parameter to the put function, that should probably be renamed to be like new S. P, yeah, I mean something to indicate like, just so when you compare these, yeah, that's not confusing. But that is the point, right, is that, like don't get confused by the right side using the same letter S. The point is that that S is bound to the function parameter here, not to the closure parameter. And one other thing we can do, if we're putting stuff into a state, another common operation is, like imagine you're using get and put. Maybe something you're doing is using get to get the value out of the state. You're computing some value with that state, and then putting the result back into the state. Right? And so modify can do that. And this is one way to implement modify. You could also implement modify with get and put. But here's another way to implement modify. The idea is you give me a function from state to state. And all I'm going to do is run your function on the state side. And return you some new SA, where the S is the new computed, the result of applying the an input state. Right, so we computed a new output state by running the function. Now, in put and modify, the reason unit is what it is there's no better type to return. Right? Like we don't have an A in either case to return it. And so in this case, if we use unit, we're just saying like, well, these functions don't actually compute any values. So like put or modify again by itself, at least on the value side, are sort of useless, right? There are sometimes reasons you use state and you're not looking at the value all the time, but you know, you're typically going to combine these states with other states to produce interesting effects. So let's look at how to use those in the code we've written so far. Here is that check cache function the way we left it off. This is one of those inner helper functions, right? And remember, short of the single, like we only did one refactoring to this method so far, right? The initial imperative code that we wrote is still the same thing. The only thing we've done is taken that cache parameter out of the parameter list and wrapped this into a closure, lifted it to a state. So what can we do here? How about this? Here's our first attempt. We're going to create a for expression. We're going to start that for expression by just reading the cache out. And we're going to use state.get. We're going to say get a cache. And now we've got that cache out. We can reference it. We're going to bind it to the variable C. Now the next generator, we're going to say state.state. Remember, state.state lifts a value. So that means the inner expression here, this whole value is going to become A. So what is the inner expression? What's the type that it computes? It says c.get of the username. That returned us that option of timestamped of whatever. Option timestamped follower stats. And we're going to use collect in this case. So if you don't know like the Scalaz collection API, basically what we're doing is saying we're going to pass you a partial function. We're going to use pattern matching. So we're going to say we're pattern matching on an option. We're going to pattern match timestamped fs if it's not stale. So the cases we're not listing here are case timestamped fs ts if it is stale. But anyway, because we only define this function, this partial function, on inputs that are not stale, the net result of this collect call, and again, if you don't know collect, don't worry about this, but the net result of this collect call is effectively we're pulling fs out of timestamped. We're mapping the option, pulling fs out of timestamped, but only for those entries that are non-stale. Okay. So now OFS still ends up as an option follower stats. And it is just an option follower stats, right? On the left side. That's bound to just an option follower stats. And so now we need to record a hit or record a miss. And so our last generator can say state.put and say if option follower stats is defined, we want to record a hit on C. Otherwise, we want to record a miss on C. Okay. I didn't show this, but C.record hit is a function that I moved to cache that just does that C.copy hits equals hits, C.copy hits equals C.hits plus 1. We saw it on the earlier slide, right? That wouldn't fit on this slide. But it's just a copy. It's not mutating the cache at all. The net result of the inside of the call to put there is that if OFS is defined, we get a new cache with hits incremented. Otherwise, we get a new cache with misses incremented. Now that we've got a new cache, cache is our state type. We want to stick that cache back into the state. So we use put is our combinator to do that. And now remember, the value, which is the left side of our generators here, or I mean the variable names we're binding to the results of our generators, is meaningless. Because remember, put returns a unit. I mean, so I could bind that to a name. I could say like u left arrow state.put, but like what am I going to do with it, right? I don't need that. The only reason we're doing that state.put is for its side effect. But it happens to be a purely functional side effect. Right? Okay, and then in the very end, I yield OFS. So this is better. Bit of a toy example. I probably wouldn't have written this function this way with combinators. But with bigger functions, it gets useful. Anybody have any critiques of this? I've only mentioned one bug so far in the talk. Well, is there anything dangerous about this style so far? What I've done here, and specifically with the idea of putting the get as the first line, the put as the last line. Right, this is really similar, in a sense, to that bug I showed earlier. Right?
OFS.
Right. Well, yeah. So OFS here, and it is like I said, OFS. The type of OFS is option follower stats, but conceptually, that part of the generator has this hidden state value that's being threaded through everything. And so, what am I doing in put? In put, I'm saying ignore the state that's been accumulated up until this point and override it with the state that I'm passing to put, right? And that's okay. But the problem here is I'm computing the value to put based off of this old C in the very beginning. So effectively, I've rewritten this function in this monadic style of all these flat maps put together in a for comprehension, but I rewrote the same bug I had initially. I mean, this does not have a bug, but it has the potential to have a bug, because if the second generator actually modified state in an important way, I've now lost that, right? Really sort of what I wanted to do on state.put is say, in this particular implementation, what I was really trying to do, right, is say, well, yeah, take the output state that was computed as part of that OFS thing and record a hit or record a miss on that. So maybe a different way to write this. We've got a combinator to do that. We've got that modify, right? Let's go back. Remember, what I'm trying to do is say, on put, compute the new state based off of OFS and based off of the state that was computed as part of OFS. So again, that's modify, right? So just start at the bottom. Don't look at the first generator yet. On the modify generator, what I'm saying is that given a function from cache to cache, I can modify the state. And here what I'm doing is saying whatever cache has been calculated up to the point that this generator runs, stick with that. But on that cache, record a hit or record a miss. Okay? So now if you think about it, if you go back to this code, that means we changed state.put to state.modify, and now C became a closure. It became bound to the inner lambda expression. But no other place on this slide do we use C. Right? The only place on this slide that we were using C was in the put. As a side note, you could have also fixed this by just putting the get one line above the put. But when you see a get and a put side by side, all of a sudden it's like, hey, that's a modify. Right? So a put puts a value. It says replace state with this new S. And a modify is just like a put, but it says compute the new value by running a function on the old S. So here we're saying modify the old cache and return a new cache. So effectively, a modify is really just a get followed by a put with a function applied to the state. Yeah. Sure. Sorry. Yes. Mm-hmm. Yeah, so what I was saying here, imagine, take that, OFS left arrow. Right here we have state.state and then this closure, right? Replace state.state with a function call that says, do something complicated that I don't know about. right? And so if I don't really know what's on that side of the generator, then how do I know whether I care about the output state of that, right? Like maybe this big complicated function that computes OFS does a bunch of things inside my state that like compute things and add things together and replace values or whatever, but it's building up and aggregating some bigger state value. And in this particular code, I'm throwing that away. Because at the end, I'm saying put back, overwrite whatever's been accumulated with the initial one.
That's what I meant by
Right.
you had something like that. And
Right.
at the end,
Right. Now maybe this is exactly what you want, right? Maybe you're trying to throw away and ignore the state that's been calculated. And if so, then by all means you can do this style. So it all depends on what you're trying to do. But in this particular case, at least with like the basic style of refactoring of like I'm going to convert from a lambda expression from S to tuple SA into a for expression that starts with a state.get. That was like the kind of the mechanical refactoring. And at the very end, I'm going to put a state.put and write my new S into it. That at least gets you into this style, but then you kind of have to look at it and say, okay, now does this make sense? Is this really what I wanted? And in this case, because state.state is the only combinator between the get and the put, there is no bug here. But if that was not state.state, it was actually something that had any effect at all on the state value, that would be a problem. Okay? Now, and so when we changed the modify now, or changed to use modify now, the initial generator needs to be a state. We could have still used, oh yeah, that wasn't true. We did use C, didn't we? We could have still used state.state, but state.state was wrapping this function that calls c.get. And so now we couldn't just move the get down below because this function was closing on that value c. So anyway, we have getS, which we talked about. GetS just said, compute a value based off the state. Give me a closure from the state to any type. You could just call it toString or whatever on the state type. Whatever the resulting type of your function is, that's what you're actually getting here. So anyway, that's what we have. We say state.getS. Given the cache, from that cache we can get out the option follower stats and do the same collect call. The net result, this is a much better way to write this than the previous slide, because the net result is that the two generators here are both completely composable. Right? They're not depending on any context around them to be implemented correctly. And now that they're completely composable and they're not depending on any context, they can be refactored into new functions and turned into their own little mini combinators. Right? So it's kind of a useful refactoring. Let's do this all again. We're going to do it with retrieve, and maybe that'll give you some other ideas. So here was our initial retrieve after we did that very first refactoring in the beginning. All we did in the initial retrieve, remember, is we got rid of the cache out of the first parameter list and stuck it into the state. And then had that inner lambda. Okay, so we're going to convert it to a for. When we convert it to a for expression, we need a way. The first generator's got to be a state. But really, the first thing, let's go back, the first thing we're doing in this function is we call a web service. Right? So the first thing we do is call a web service, take the output of that web service, wrap that into this timestamped value, and then update the state. Now clearly that last part of let me just update the state, we could do that with a modify. Right? We could do a modify and just call _.update. But now what do we do with all the stuff before that? Right? Now we could create we could implement this as saying retrieve, use string, whatever that first line and second line. But on the end of the second line, instead of saying equals state open brace C arrow, we could just open a block, just a normal brace, and then say val fs equals call web service, val tfs equals timestamped fs now, and then just return state.modify _.update. But that would be really bad. Because if you think about it, what that means is that you're really going to end up using retrieve as a combinator in a series of state expressions. Right? You're going to have this program built up from all these little mini state combinators. You're going to wire them all together. When you're building up the program at runtime, when you're flat mapping all these methods together, you're going to evaluate the web service. But that's not what you want. You want to say when the state is run, evaluate the web service. So you don't want to pull those values outside of the state action. You want to keep the computation inside the state function. So, so we want to leave that and say the whole thing should return a state. Inside of that state function, we want to do these two vals. And when we convert that to for expression style, we would do it this way. We would just say call the web service, that computes some value, and just lift that value directly into a state. Right? Remember that state.state combinator we wrote earlier. We just lift that value directly into a state. We can immediately bind to the value ignoring the state with fs. We're going to just create TFS equals. TFS is not a generator, it's just a name binding, to the timestamped wrapper. And then we'll do our state.modify. Okay. Any questions on that refactoring? Okay. So that's about the halfway point of the talk. We're basically on time. We're running a little late. So let's see now. Short of one example that I can think of through there, everything else we did was pure Scala, no libraries. I think the only example that used Scalaz through that was when we did the OFS question mark to say is defined. And again, because I can't fit it on a slide if I don't use that. But it has nothing to do with states. Like everything state-wise we did is completely standalone. As a side note, if you look at the code for today's presentation, everything we've done so far is in the Scala files 1 through 5. So 1.scala starts with where we started, very imperative-looking code, and then successive refactorings up through 5. So if you want to play with things, or start with 1 or 2 and try to do the next step in the presentation yourself, I totally recommend it because I think it really solidifies these ideas and gets you used to thinking in terms of functions and all that. And you can see that here. Like here's our first example. Very, very, very basic. But anyway, this also defines things like cache, which I didn't put on the slides at all. And if you jump all the way to where we just finished, you can see things like record hit, record miss, that kind of stuff, state.modified. And again, this is using SBT. So if you just come into the repository, run SBT, and type console, once it comes up, you'll get a Scala console with all this code loaded. We can say import training.first example, and then play with these things at the REPL. Okay. All right. Oh, and one other thing, at least so far, there is a simple state example in here that is the implementation of our state data type so far. Which again, we don't have to look at this. We've already looked at this code, but this kind of puts everything in context, lets you play with it, lets you change this stuff, etc. And this does not use any libraries. Okay, so let's move on to Scalaz. Scalaz provides this. Some of the function names I chose, well, I chose specifically because those are the names Scalaz uses. So if you just get rid of our custom state data type and use Scalaz state data type, all these examples work. And so anyway, for something this simple, when state really is just map and flat map, why would we want to use it? Why would we want to pull in a whole third-party library just to do this? And the answer is this stuff. As everybody probably remembers from the last time we got together, Scalaz's got this whole wealth of fundamental type classes like functor and monoid and applicative, and when appropriate, state integrates with all of those built-in type classes from Scalaz. There's also some really interesting set of integration with lenses, and we'll look at a little bit of that today. And then there's also some nice integration with this thing called monotransformers, which Scalaz provides as well. So we're going to run through that stuff now. So let's start with just some conveniences. Scalaz has these eval and exec methods. Basically, when I said when you call run, all run does is you give it the initial state, it invokes the function on that initial state and gives you back S and A as a tuple. Now maybe sometimes you don't care about both of those output values. So we've got eval. And what eval does is it just says, throw away the output state. I don't care about it. Like the only reason there is an output state in this computation is that internally, all of those combinators that were working together, all my little mini functions that operate on the state, they're all communicating with each other through state mutations. But at the end of the day, I'm really running this program to compute some integer or to compute some follower stats or whatever. So eval is literally just a wrapper for run that throws away the output state, just ignores it. So you don't have to pull it out of the tuple or pattern match or whatever. And exec is the opposite. Okay? Exec says, the whole reason I'm executing this program is just to get at the computed state in the end. I don't care about the output value. And an example of this is that modify or the put, right? At least in the micro sense, when we look at just that state.modify combinator, the output value was a unit. And if that happens to be like the total computation that I'm doing is a state of some state type to unit, I don't care what I output. And so anyway, eval and exec don't, they're not particularly interesting since they're just throwing things away in the tuple. The reason I like them is that it really exposes the intent. Like when you look at, state code, you pull up some coworker's work or whatever. If I see a run, then I'm looking at like the pattern match, or we're actually accessing the members of the tuple directly. But anyway, either way, whether I'm accessing them directly or I'm pattern matching on the resulting tuple, maybe it's not clear to me when I first look at it as to whether, why you used run and why do you have these two output values and all that. I can use eval and exec and expose my intent very easily. Another thing that's common to do is to start a computation with the zero value, the zero element of a monoid. So if my state type happens to be a monoid, I remember what a monoid is, right? Semigroup with zero, and a semigroup has append. Right? And we talked about all those lulls and all that in the past. So if my state type is a monoid, maybe what I really want to do is say start with the zero value and run the whole thing. So I've got three additional methods, run, eval, and exec zero, that can do that. So for example, I can provide a monoid instance for cache. So let's look at that. I didn't put this in the slides. I don't think. Okay, let's just look at that. There's a monoid for cache, right? I'm importing the fifth example. So basically everything we've done up to date, I've got imported. Okay? And I'm also importing scalaz.monoid. My zero element of that monoid is just a cache with an empty map, no hits, and no misses. And my append operation is just going to say merge my two maps together, merge my hits, merge my misses. Make sense? So anyway, now that I have this monoid for cache, very, very, very simple to implement, I can just call run zero and run a whole computation. I don't have to manually pass through cache.empty or whatever. So again, it's just syntax stuff, but it's nice. What else we got? There was a bullet point earlier that said when you fix the state type, right? If state itself state itself takes two parameters, state type parameters, S and A. If I fix the one and let the second one vary, so I fix S, let A vary, the net result of that partially applied type is a monad. And I'm not going to prove that it's a monad, but it is. And anyway, and so Scalaz's state type, when you fix that cache value, or the S type to a specific value, has integration with pointed functor applicative monad. Okay? And I'm going to show you some examples of that. So let's do it. The simplest way to fix the state type to a specific value is via a type alias. You do not need a type alias. But without a type alias, you're going to have lambda type expressions. We've looked at those before. They're big and they're ugly and they're a lot scarier than they need to be. So a simple way of doing that is just to define a type alias. So here we're going to say we have state cache. State cache is going to be parameterized by a single type A. And now if you look at the definition of the state data type, the A parameter is covariant. And so in order to get full benefit of that variance, we need our state cache type parameter to be covariant. That's what that plus does. But anyway, if I have some type state cache that is parameterized on some type A, I can alias that to be state of cache comma A, right? Totally makes sense there? And then I can do really nice things like I want a pointed instance. So I just say pointed of state cache, and now I can use the point function. So let's just look at that one line for a minute. Does everybody remember what pointed did? What pointed did was it lifted a value into a context. So let me use an example, option. Right? We looked at this in the past. Option, we need some way to say, given any value A, how do I get an option A? How do we do that? Forget Scalaz. Given an A, how do we get an option A? Wrap it in sum, right? That's all you do. So anyway, you could hard code that in your code, right? You could say, you could just wrap it in sum yourself whenever you want. If I have an abstraction, though, that says any one of these types that have a single type parameter, any one of these abstract types that have a single type parameter, like option or list or, in this case, state cache, if they all have something in common, perhaps, where they can go from an A to a f of A, whatever the f type is, can I abstract that out into some new type class? And Scalaz provides pointed for that, right? So quick code diversion. Here in Scalaz, I can say, I got to import, sorry. Oh, you know what? I have this already over here. So here in Scalaz, I can say pointed of option dot point 55. Okay. And we get sum 55 back as type option int. I can do the same thing with, let's say, list, which is also pointed. I get a list of one element, 55. I can say type state, or let's say state int plus A, like we just did on this slide, equals state, where the state type is fixed to int and varies over A. And as a result, I can say state int dot point 55. What did I get back, right? I got back a state. I got back a state whose s value is an integer, or whose s type is an integer. And so a net result of a state is I can run it, right? So I can say run, and I'm going to pass in, well, let's say we'll run 0 because int's a monoid. So if we run, well, okay, I'll just run for 0 now. If we run it, then you can see all it's doing is saying, given some value 0, I had the output of 0, 55. If I run that same thing with some output, let's say minus 21, I get back minus 21, 55. If I run that same thing again with 100, I get back 100, 55. What is that? That's state.state, right? It says this state is a combinator, is a state instance that says, given some input state s, just return whatever you pass me as my output state, and I'm going to fix the value to be a specific value. So state.state, that thing we drove as part of the first part of the talk, really is the definition of point for the pointed state type. Run 0 will work. The reason run 0 didn't compile there is because it's not in Scalaz 7 milestone 3. It's in trunk, or the Scalaz 7 branch. So you have to actually have it be running with a snapshot of it to get run 0 to work. Eval 0 does work, but well, anyway, we would look at that later. Okay. So anyway, that was just a bit of a diversion, but the point here is by fixing that one type, I now have integration with all these nice type classes. Some other nice things here is that if you import Scalaz syntax ID, right, and you remember using the Scalaz 7 module design, I can actually enrich my types with additional methods via the syntax package. So here, scalaz.syntax.id says enrich any type. Given any value of type A, add methods to it. In this case, we're adding the point method to it. So given anything, we can, as long as we have that import, we can just call .point on that and then specify what type we want it wrapped in. So again, from the command line here, 10.point option, 10.point list, and so on. Okay, same thing. It's just syntactically a little different. And we have a functor example, right? Remember, a functor is something with map, given a function a to b. So here, if we had some state called 10, spelled out ten, we could get a functor for state cache, call map on it, which would take us from whatever a value it was to b, and give us back a state cache of b. In this case, we're converting from whatever a it was to a toString. So theoretically, maybe this 10 thing represented a state whose a was an int. We're calling a toString on it. This is the same as the map we looked at earlier on state, right? The nice thing here is that anybody can write code that just deals with functors. They don't have to write code that's specifically statically binding to the map function on the state data type. Okay. Maybe something that you might run across, rather than accessing pointed or functor directly in your code, something that you would run directly into your code is this. And this builds off the fact that state's an applicative and traversable and all that, or a member of traverse. So, oh, that's not entirely true. But anyway, so in this first example here, we have list of state. And we're calling follower stats 3 times. And putting the results into a list. The first time we call it with the string or with the username u1, second time we call it with u2, third time we call it with u1. Right? It's not clear to me, at least so far, how we do anything useful with that list. Right? We could map over the list, get each individual state back, run each individual state. But now I need an initial value for state for each one of those initial list entries. So instead, can I wire them all up such that the output state of the first follower stats call is wired to the input state of the next follower stats call, is wired to the next, the output state of the second one is wired to the input of the third one. Right? If I just mapped over a list and passed the same initial state value in for each of these entries, they're all going to be a miss. And clearly here, the third call should result in a hit. Right? Because I'm using the same username again. So anyway, I've got a list of state cache. I want a state cache of list, is really what I'm saying. I want to combine all, that list of state caches, combine all those things into a new thing, a new state, that when I give it a starting cache value, as a result, I get an output cache value and I get a list of my actual follower stats. And that's what sequence does. Remember, we've done sequence before, just inverting the 2 types. So anyway, that does produce the right output.
Calling followers stats, you're not actually code.
Right.
That's just you haven't gone.
Right. None of those effects actually occur until you call run. Now, you don't care about that, typically, if everything's purely functional. right? If I have full referential transparency, Follower-Stats is like a pure functional, it's implemented pure functionally. That doesn't matter necessarily, at least from a reasoning perspective. But like I said before, we were like calling a web service, right? So this is not pure functional code. And so when things happen does matter. And hence why, earlier we talked about how like when we call that web service, we got to make sure we're doing it from within the state function, not, as part of computing the state instance. Sure. You want, basically defer the run until you've combined your whole program together into a big state. Anytime you run, you're breaking out a state, right? Sort of like calling like get on an option. Like you're breaking out of the data type, and in the case of state, you're actually affecting, like you're saying, invoke all my functions now. Any questions so far? Okay. So far, so good. We talked about mapping on A, right? On the state itself, we can just map a function. So we can have, given a state of SA, we can go to state SB if we have a function A to B, because it's a functor, right? If I get my whole application wired together into this big state function, I'm going to need something like this, right? I'm going to have to represent everything my application needs. Every function anywhere is going to have to be represented in this big S data type. And now I don't want my function that happens to read from a cache to have to know about my application state, right? Like if my application state's storing stuff for other subsystems or whatever, I want my small function that just reads from a cache to use the cache S type. But I want to be able to compose that into a bigger application where the state type is bigger, right? So fundamental, our fundamental action with functional programming is this composition approach. So how can we compose these state data types in a way that we can transform the state type? And so really what I'm asking is this. If I have a state of t comma anything, how can I just treat that state as a state of s comma anything? Okay. So we're going to derive this. And as a side note, all these times I'm using a question mark for the type parameter, I'm really just saying that we're letting that type vary. So like that doesn't compile in Scala. You can't use a question mark. You'd have to either use a type lambda, those big ugly type lambdas, or you'd have to use a type alias like we just did a minute ago with state cache. There's this really cool project, like just kind of got some more visibility in the community over the past couple weeks that would actually make that compile. Basically, it's a compiler plugin that sees the question mark and just turns it into a type lambda. It's pretty neat. I'm pretty sure the author is from Philly, so if you attend users groups in the area, you probably know him. Okay, so this is what we're trying to implement. Let's implement this function. We've got this lift, and given a state t of a, we want to return a state s of a, right? So let's start this way. Using just what we know so far, what we can do is create a new state, and now we got some input s, right? Now we don't have an s. We don't have a state of SA right now. We have a state of TA. So I can call run on the state TA. But in order to do that, I'm going to need an input t. And the result of calling run on a state TA is an output t and some a, right? So at least that middle val is pretty straightforward. That's the only thing I can really do, sort of like map and flat map. It's like the only thing I can really do with that state TA. Well, right, where's input t coming from, right? And I've got this input s coming in, and I know because I'm trying to return a state SA, I'm going to get an input s And as a result of this, I've got to return an output s, comma a. So if I kind of like, cast it in this structure, I've got some errors here, obviously. I need a way to fill out input t and output s. And one way to do it is this. What if we could imagine a function called get that, given an input s, can just give us an input t? Right? And same thing with set. If I could imagine a function set, I thought I fixed that typo. It's fixed on the next slide. There's a typo there in set, but the idea of set is that given an input s and an output t, I can create a new output s that has t applied to it. I can make this work, right? Now, clearly back here, I can't do it. So, like, this is just normal abstract reasoning, right? Is that I have to fill out input t, I have to fill out output s. I can kind of get an intuition that this feels right. So I just create something, I create two functions, get and set. I don't have those two functions, get and set, so this won't compile. So just give them to me. Okay? So I just abstract this whole thing away. Now I wrote the function. And this is a way to do it. So if you give me a state t, and you give me a function where I can convert an s to a t, and you give me another function where I can say, given an initial s and a new t, give me back a new s with that t applied to it, then this code is implemented, right? That's pretty straightforward. So now given this, if I have s and I have get and I have set, I can now compose these bigger state functions and mutate my state type and get bigger and bigger and bigger as I get higher and higher and higher in the layers of my application. So what is a get and a set, right? It's lens. I know we haven't done a lot of work with lens before, but I can just take that get and set, replace them with a lens, and then down below in the body, I'm just replacing get and set with l.get and l.set. Right? And in fact, I get a bunch more power when I do this, because lens is more general, at least in the Scalaz implementation, and certainly the theory of it. It's much more general than just that get and that set function. Now, there is a way to construct a lens with just a get and a set function. Right? We've looked at that before, lens u. But anything that's now a lens can now help me go from a state t to a state s. Okay? So this is so useful and so common, it's provided. There's a function on lens called lift s. Lift state is what the s stands for. Okay? And so you actually wouldn't have to write this method at all. Right? So by the time you get here, you say, oh, well, it's already provided. You delete your method and just use lens.liftS anytime you need to make that conversion. So that's really, really nice. And there's a bunch of other things where lens and state kind of have a really close relation between them. A lot of ways that given a lens, you can get a state out of it or convert it to a state. Like a lens can be treated as a state directly, and it has a certain behavior. So I'm not going to cover them today. If you want to see all the other ways that lenses interact with states, there's a really good talk by Edward Kmet. I think he gave it at the Boston area Scala users group like a year ago or so. And it's on YouTube, and if you want the link, just see me later. But he goes through all the additional ones. Also, in Scalaz, all of this is implemented. So if you look at, if you look at lens in Scalaz and you just search for like state t, you'll see there's a bunch of different functions on lens that will give you a state back. You don't have to read through these to understand what they do, or look at Ed Kmet's talk, because he goes through a lot of these. Okay? All right. And that's the definition, by the way, from the Scalaz source code of lift_s. So I'm not going to get too much into the details of that type signature in the interest of time. Okay, so another thing we can do is integrate state with other things, like either. So let's look at this code. Completely new example. Not using state, okay? So imagine this. Maybe we've got some type of query service where we can query some model in memory. So I've got some trait called model, which I'm just deferring the implementation of that, right? I'm not worrying about implementing model right now. I've got some trait called stats query, some trait called query result. As a side note, at least something that I find personally useful is when writing this code like this, or any functional code. When I first start, I might create these traits and not define them and not provide any implementation of them, just to figure out the algorithms, just to figure out like the way all of the functions are going to come together, and then later figure out the details of what is a model, or whatever. And as I'm coding, if a model is supposed to have some function when it called get foo, then maybe I'll just come to the trait definition and add def get foo, return the right type, and then keep going. And you can focus on like the program structure. Eventually get the whole program structure to type check, then you can come back in and replace this trait with maybe a case class or whatever it really is. Right? Anyway, so imagine we've got this now run query method. Given a string and a model, it returns you either a string or a query result. So this is actually new for people. I think the last time we all met on Scalaz was before this was added. But that little v, right, it just means either. If you use Scalaz built-in either a lot, you know how you can't use it in for comprehensions without projecting. So if you wanted to use either in a for comprehension, you got to say .right on the end of each line, just to say like, hey, when I call map or when I call flat map, I'm actually calling that on the right side of this value or the left side of this value. In Scalaz, they provide this data type v, standing for like logical disjunction, which is completely isomorphic to either, except it's right leaning. So map and flat map work on the right side. In that result, you don't need to call right all over the place, and there's a bunch of other nice things too. But anyway, so now imagine I've got this code. I've got parse query that either returns a string or a stats query. I've got perform query that either returns a string or a query result. And I can combine them in a very natural way with a for comprehension, right? Everybody's used to code like this, right? So now my question is, requirements change. And now it turns out that like parse query and perform query need some state to compute their results. I think in Edward Clement's talk, he makes a joke like, well, the way you would do that is just add that big mutable bar, right? Like I started with our first example. Like if this happened to you and you had this whole program written and it was beautiful and you're proud of it, and boom, all of a sudden you need some piece of global data way down deep. Maybe the way you do that is just kind of cheat and stick it there and hope you never call it for multiple threads, or you synchronize on it and all of a sudden you've got scaling issues perhaps, whatever it may be. So my question here is, how can we change this? How can we refactor this existing code so that we're using state, we get all the benefits of what we talked about, but not have to like completely rewrite this stuff? Okay. So what if we do this? We've got some data type. In this case, I'm just going to use a trait. Like I said before, I'm just making a placeholder data type. In reality, maybe query state is going to be some fancy case class with all my real data that I really need to do my computations. But for now, I'm just going to create a trait called query state and not fill out the details. Now I'm going to create my type alias and say query state s varies on a, and it's really equal to state of query state and a. Okay, so this is exactly the same as we just did earlier, except instead of cache, I'm using a new data type called query state. Right? I picked a naming convention I use a lot where I just put S on the end to say this is the state monad for my data type called query state. Okay. Now I start refactoring. And I say, well, now run query can't return a string or a query result. It's got to return that thing wrapped in a state. So I can do query state s of string query result. As a side note, the type alias, of course, if you've got a lot of functions that are using the same state value, you don't have to write that out all the time. You just use the type alias. So here I'm using query state s as the return type and just saying the a side of my state is string or query result. Well, so this doesn't work, right? Like forgetting the implementation of parse query and perform query, the problem here is that line. Because what's the result of that line? Right? Because, if I go back a minute, if I look at this slide, back before state was involved whatsoever, my flat maps here are the flat map on either, on the V data type. And so what's the type of query? Like that variable query on the left side there, what's its type? Right, stats query, right? Because you're flat mapping through, and the right biased either provided by Scalaz says I can break out of this computation, in a sense, and I'll let you worry about just the right side. And as soon as I hit a left, I'm going to break out. So in this case, query is a stats query, and res is a query result. But now, when I switched everything, I wrapped everything in a query state s. The variables that are being passed in the flat map calls are now the a from state. And my a from state in this case is that big disjunction, right? Is string or stats query. So this doesn't work. Well, that kind of stinks. So how do we kind of get both? How can I keep my flat map, my code, that top-down, very logical for comprehension, but get the benefits of both state and disjunction and either? And the answer is that there's this data type, kind of funky data type called either T. And don't worry too much about the way it's defined there in that f parameter. But basically what it does is it represents a value, A or B, wrapped in an f. So for example, if I have an A or B wrapped in an option, I could use either T, where the f is option, and the A and B are A and B, right? So anytime I have this, anytime I have a type constructor of one type, like option or list or whatever, and I want to, and I have a value of that type on another type, I can use either T. Now, what does it do? Well, it's this idea of this thing called a monad transformer. And the idea of it is that it composes the effects of either, of disjunction, with the effects of an arbitrary monad f. Okay? Now, it turns out, monads, like there's a phrase, monads don't compose, right? Generically, completely generically, given two monads, if I have two different instances of the monad type class, maybe I have option, I have list, or I have, let's take option list. If I have option and list, there is no way I can write a generic function that says, given monad 1 and given monad 2, create me a new monad out of them. But what I can do is say, well, maybe list monad has some special properties where list can compose with any other monad. So I could write a function or a type that lets me treat a list of any inner monad type as a monad. And that's something called monad transformers. And this is kind of like the big scary topic in Scalaz. A lot of people struggle with monad transformers, and I struggled a lot with these. But there's a lot of good references, and most recently there was a talk given by J.R. West that covers these, I think, in a really good way. And there's a link here in the slides for that, where he goes through the whole history, and it's a good video and set of slides on this. So I'm not going to talk about like the theory behind monad transformers. What I do want to show you is how to use this either T thing to accomplish what we were doing. So I said either T wraps an f of A or B. What do we have? Right? We have query state S, and then we have a string or query result. Now query state S, remember, because we have that type alias, remember what I said earlier, if we fix the state type, then the resulting partially applied type constructor is a monad. So we have a monad for F, and we have an A and a B. So we can represent that like that. Okay? just type-wise, right? Now, this is a different type. Either t is a completely different type than f, a, or b. But the point is that I can use either t with those three type parameters applied to wrap query state s string or query result. Okay. So bear with me. This is the toughest slide in the presentation. But there's really not a lot here when you really break it down. We have that query state s type alias that we looked at a minute ago. It just fixes the state type s, right? I define a new type alias called et, short for either t, right? And what I'm going to do is say either t is a shortcut that I fix the a. Okay? So what I'm doing here is fixing a to string. So et now represents either t across any other monad f where that monad wraps a value of string or something else a. Okay? And I'll show you why we did that in a minute. And I'm going to create a third type of alias, query state es, for query state either followed by state, right? Is the naming convention there. And what I'm going to do is say apply the query state s monad to et. But I still don't know what my value type is. Okay? So I'm going to make that a parameter, a. So the net result of this is query state es takes a single type parameter a and just represents string or a wrapped in a state, or sorry, either string, sorry, I said that wrong, string or a wrapped in a state, lifted to either t. And I'm going to create a couple constructors for that. I have the three constructors. We're only going to use one of them today, but these are three that I typically end up writing. I'm going to create a companion object for query state es. And the first one is just our normal apply. And remember what I said earlier is either t wraps an f, a, or b. So to apply, to create a query state es, give me an f, a, or b. And I'll just call it the apply on either t. Right? So there's nothing really fancy there. I don't need this method, this apply method, right? I could just call either t apply, either t open paren, or either t brace, or whatever. But since I know all these types, like I know in this particular code, my left type is a string all throughout my code. I'm going to keep it to be a string all the way throughout. And I know my monad in this case is query state s. Rather than deal with failures in Scalaz type inference in various ways and have to specifically apply all those states, I can just put this all in this one place in this apply method. And then any place where inferencing might fail, I can just use query state es to construct either with the right type parameters. Okay. But anyway, query state apply is just lifting the query state left or right into an either t. Then I have lift e that says if all I have is a disjunction, if all I have is an either, it's just a value, right? I need to get that value into a state. And if I have that value in a state, then I'm good because I have an either in a state, and that now is what I need. I can take that state that wraps an either that wraps an a or a state that wraps an a or b, and I can lift that back into either t. So the implementation here, you can see, just uses that point that we talked about earlier. It could also have used state.state. But it basically says take the either and point it, which now gives us a state that wraps an either. And then call apply, because apply does that exact thing, right? Given a state that wraps an either, it can give you an either t back. And now there's one other, at least there's one other one that I run into a lot, which is, well, what if I don't have an either? Right? What if I just have a state on some a? Like maybe it's a computation that can't fail. It just returns me, an int or a string or whatever. But I need to make it interoperate with these bigger for comprehensions. And so there's a couple different ways you could implement it. I happen to use lift m here, which is a predefined operation on monad transformer. So there's a type class in Scalaz, abstracting a whole other level up now, that says either t is a monad transformer, either t is a monad transformer when the left side is fixed, which is why I define that et type class, or type alias. And hence, there are operations you can do across all monad transformers. And one of them is this lift-m operation, which has this signature that just says, given a G of A, as long as G is a monad, I can turn it into an FGA. An F parameterized on monad type G and value type A. And if you pull together all the types on this slide, you'll see lift-m is exactly what we need. I won't go through that now. But the interesting thing here is that just like I said, pointed, functor, monad, genericized functions across all monad types. Monad trans genericizes functions against all monad transformers. So lift-m wouldn't have to be implemented all over the place. And in presence of a deeper, a richer type inferencer, you wouldn't need these methods, or at least not lift-s and apply, right? Because lift-s and apply are just calling predefined methods. And the only reason I ever define these aliases for those methods is to help the inferencer in cases it can't figure it out. And by the way, when you do this, when you have these nice little type aliases and these nice functions that just wrap existing functions, you can do all of this stuff without ever writing a type lambda. So if you really are adverse to that syntax and you don't like it, you don't need to use it. Okay. Anyway, there's my program. Run query didn't change, right? It's the exact same implementation. The only difference is that instead of returning string or query result, we are now returning an either t that wraps a state. We're now returning an either t that represents a state that wraps a string or a query result. So the first refactoring we tried was to say, well, just wrap string or query result into a state, and that failed because the flat maps didn't compose the way we kind of had an intuition for the way they should compose. And so we've made one slightly additional refactoring here, is instead of just returning the state that wraps an either, we're now returning either t. We're just lifting that state that returns an either into either t. But you can see it doesn't even change the signatures that much when you have these nice type aliases. And now as a net result of that, when I run the query, I have an either t. And so how do I go from an either t back to a state either string or whatever query result? And the answer is via run. And if you call run, you now just get state of string or query result. But now that I've got a state, I've got to run it somehow to actually get that inner value out. And so I'm going to run it again. I'm going to call run on state, passing an initial s. So anyway, that is the most complicated part. If you're interested or you run into the need for this, I definitely recommend that one presentation I mentioned, and feel free to contact me. Okay, there's one other topic. We're basically on time. We're going a little bit over our 2 hours, but we'll definitely be done before 12. One other topic is that there happens to be a state transformer for state as well. Okay, and it turns out that Scalaz doesn't actually have a state data type. Scalaz only, in this case, only defines state t. And then it has a type alias that says a state SA is really a state t whose monad that it wraps is the identity monad. And the identity monad is a monad that does nothing. And you can see when you look at the apply method on state, so all these places where we've been saying state open brace s, right at the very beginning of the presentation, it tells you a return state of SA. And in your error messages and stuff, generally you'll get messages that ignore the fact that this thing even exists. But if you were to reflectively call a toString like we did earlier at the REPL, and we saw state t of ID, this is what's actually happening, is that it's when you call that, instead of just saying new state of SA and then defining that apply method, what they're really doing is saying return a new state t where the monad is fixed to identity. Okay. And this is sort of the way it's done. State T is defined to take a type constructor F and then S and A. Identity is a type alias. ID of X is defined as X. So it's kind of mind-bending, I think. It's almost like I'm lifting my type X into a type constructor of one parameter and then immediately ignoring it. Well, it's not the right way to say that, but it's kind of a mind-bending idea. And then they have that type alias for state. So don't worry about too much about the way that works. But the cool thing about doing all this, it doesn't change anything we've talked about. So if you never need state T, just delete the rest of this presentation. But the cool thing is that because state is the state transformer, we can use it with monads other than ID. And so let me give you one more example, and then we'll be wrapped up. It's this get an increment. So imagine a very simple example, get an increment. The state type is an integer, and the value type is an integer, hence state int. And it'll be a state action that when given an input S, increments it in the state, but returns S. This is like S++, right? Actually, I think even Edward Kmet mentions that in his talk. It's post-increment, right? Return the value and increment it, but return me the value pre the increment. Okay? And now I can use that. I can say, do it 10 times, and then eval it starting with 0. And you'd have to look at what replicate M is. But basically, replicate M is defined such that basically anything that's a monad, I can say, do it n number of times flat map to itself. Right? So really what I'm doing here is saying, get an increment, flat map, incoming, another get an increment. I keep doing get increments 10 times. So what's the net result of that eval 0 is I get that. Okay? So if I, basically the first increment, or the first state computation returned 0 because that eval 0 started at 0. It returns 0, and then replicate M moves on and says, okay, do it again, feeding the output state of the first invocation in to the input state of the second invocation. So the second time, it returns 1 and increments the state to 2. And then the third time, it returns 2 and increments the state to 3, etc. And then what replicate M does is at the end, it puts it onto a list. Each one of those values that were returned while we were flat mapping through, it preserves each one and returns it as a list. Okay, so that is, and don't worry about replicate M, that's what that evaluates. So my question is, what does that evaluate? And you would think it would be list of 0 to 1, 2, 3, all the way up to 9, 9, 9, 9, 9. Right? You get a Stack Overflow. Why do you get a Stack Overflow? Yeah, right? When it's that replicate M is doing its job, it's doing all those flat maps. And each one of those is another call to flat map. And it's building this huge call stack as it's recursing through all these flat map calls. And so when we do it 10,000 times, it blows up. So basically we need a way to do almost like tail recursion or some type of recursion elimination where that replicate, or in general, where state, as we're flat mapping, can do that without stack usage, or at least some type of limited stack usage, right? So it turns out there's this really interesting data type called free, or the free monad, and it's really a monad transformer parameterized on a particular type. We're not going to get into the details of this, but basically there's this type alias trampoline, and a trampoline is really just free with the typing function 0. I shouldn't say monad transformer, that's not true. But anyway, and the net effect of this is that with trampoline, or with free fixed on function 0, it can do monadic recursion or monadic binds without stack usage. Or you only need enough stack to do one bind effectively. and you keep trampolining out of the bind internally rather than all these nested flat maps. I am not going to, I didn't even explain that well, and I'm not going to give you the theory behind that. There's a couple really wonderful write-ups on that data type. There's a blog, Runar's blog from a couple years ago, as well as a paper presented at Scalaz 2012 that talks all about that and starts with a very simple, I think he starts with state, in fact. Starts with a very simple example and builds up step by step by step, introduces delimited continuation-based trampolining. So everybody remembers Dick Wall and Bill Venner's example of delimited continuation-based trampolining, right? Maybe not. It was like the end of the time they were here. But anyway, it's that idea, but then Runar keeps genericizing it until he gets to this super, super, super general state. The important thing for us is that the trampoline, or in this example, the trampoline data type, we can put as our type in state T. So if we replace ID with trampoline, we can do that whole computation without stack accumulation. So anyway, this is what it looks like. Get and increment did not change whatsoever. Get and increment stayed as a state of ID, or state T of ID int. We import this trampoline type from Scalaz, and then we call lift on state. So remember, this is get and increments returns us a state of int. We're saying lift that into a state of state T of trampoline int, and then run it. The net result of this is that eval 0 here, instead of just returning us the output A, now returns us a trampoline that can compute an A. So at the very end, we got to tell the trampoline, go do your thing. So at the very end, this call to run right here is where internally the trampoline's going in and out a bunch of times for various flat maps and computing the value. And trampoline scales perfectly. Unrelated to state, completely unrelated to state, but I have an application that I was working on that's using iteratees, which some of you may be familiar with. But basically, we were using iteratees, and iteratee has a has a monotransformer, iteratee T, and so I was just using iteratees to say generate like a stream of, let's say, strings or something. And it worked great until in this one application, it's like downloading something, and it's writing a bunch of strings to the iteratee, giving status on the download. And everything worked great in the application until we implemented like ANSI style downloads, where instead of just like a regular progress bar, it was like being updated like thousands and thousands of times with all these little strings that say like go back and redraw that line with ANSI escape codes. So anyway, the net result is the iteratees went from like things that produced like maybe 10 elements and then we're done to things that maybe produce 10,000 elements and we're done. And when you look at the way iteratees are implemented, really, it's a series of flat map calls. We ended up with the same problem. And I was sort of depressed because I thought, like we're going to have to rip this out. And it's like this huge impact to the application. And all we had to do is change from using iteratee of like string and whatever the example was, to using iteratee T with trampoline. And then making that one extra run call. And boom, the whole application no longer had Stack Overflow errors. So this, I actually have run into this in real code. Okay, so anyway, that's all we have. Any questions?